Good afternoon. I am Graham.
I'm Jonathan.
And today we will be working through quicksort
And binary search.
So to start off, we have a 9-integer array. All of the numbers are jumbled up inside of it, and we're going to use quicksort to solve through it. Now, with quicksort algorithms, it's very similar to a divide and conquer mentality. So we start by setting our lowest and highest bounds. Now in this array, since there's 9 integers, the lowest is going to be in the 0th position, and the highest is going to be in the 8th position. Now we look at it and we try to find the middle to determine our pivot. The middle of this is 5, since there's 4 on one side, 4 on the other, so the middle has to be in the 4th position of the array. So with this, we look at I, the lowest bounds. If the lowest bounds is less than the pivot, you increment and you move I to the next position. But since 12 is not less than 5, it remains there and holds this position. Sorry. So with the highest bounds, you look at it, and if it's greater than the pivot, you decrement. And since 20 is greater than the pivot, it decrements down. But since 1 is not greater than the pivot, we look at these, they both hold positions. Now if this one is not less than and this one is not greater than, we swap. So that goes there, that goes there. These then both increment and decrement. And since 6 is not less than 5, it holds its position. 15 is greater than 5, so it decrements to 7. And 7 is greater than 5, so it decrements. But since 5 is not greater than 5, these both hold their positions, and they have to swap. So the key stays. Now, since we have the key here, we now look at these 3 values. So we set the lowest to there and the highest to there. So we look at it. 1, since it's less than 5, increments in. 3, since it's less than 5 and not greater than 5. And since 5 is not less than 5, these have to swap positions. Pivot stays. So now that we have the lower portion of the array set, we now look at the upper 5 integers. So we set our lowest bounds at 9 and our upper bounds at 20, which is the 3rd position and the 8th position. And the middle of this would be the lower of the middle 2 cups. So now we compare. 9 is not less than 7, so this holds its position. 20 is greater than 7, so it decrements to 12. 12, again, greater. 15, greater. But 7 is not greater. So we take these and we swap. Now we look at these 2. Since this is the key, the lowest bounds is going to be 7, and the upper bounds is going to be 6. Now, since 6 is not greater than the key, and 7 is not lesser than the key, these have to swap. And just increment. So now that we have these 5 understood, now we look at these 4. So our lowest bounds is 9, and our upper bounds is 20. And our pivot will be set at 15. So we look, 9 is less than 15, so it increases. 20 is greater than 15, so it decrements, but 12 is not greater, nor is 15 lesser. So these switch. Now, since we have all of our array understood and followed through on, it's all organized, it's all set up. The program will run a couple times through to make sure everything is set, but in its entirety, the array is now organized.
All right.
So,
and now I kind of understand what you meant by divide and conquer. You first find that pivot value of 5. You arrange the array so that the integers less than 5 are lower originally. These can be scrambled, but they're all higher than 5.
So
you look at that. I see. That's a nice algorithm. All right. Shall we learn how to do binary search?
Of course we shall.
All right. Sounds great. So with binary search, you have to start with an array of integers that is already in sorted positions. So as you can see, our quicksort put them in the sorted order. Now we are ready to call the binary search. With binary search, what you do is you send the algorithm the key that you're looking for. So today, let's look for the integer 15 in our sorted array of integers. What you do is you always start with the middle element of your array. So that in our array of 9 integers, that is the fifth actually. 0, 1, 2, 3, no, fourth. So we look at the fourth, does it equal the key? No, it doesn't. It's less than the key. So since it's sorted, we know that these are all less than as well, so we can disregard those. Now what we do with the remaining array is we find the middlemost element of that array, which happens to be 12. Is 12 the key that we're looking for? No. 12 is less than. Since the array is sorted, we know that these for sure won't equal the key, so we disregard them. Now we go to the middlemost element of our remaining array and we compare it to the key. Does 15 equal the key? Yes, it does. This is what we're looking for. Let's return the index value of the array where we found the key, which happens to be 7. So if you're looking for the number 15 in our 9 integer array, you can find it at index position 7.
Now, John, we've seen it with an upper value, but what happens when, say, from the middle, which is 7, we happen to have a value like something 3, which is lower than?
Sure.
How does that work?
In the prior example, we disregarded the lower portions of the array. So let's say we're looking for our key value to be 5. How do we find it? Same thing. We send the binary search algorithm starting on the sorted array with the key value. We always start at the middlemost element, 7, which is in position 4. 7 is greater than our key, so we know that all elements to the left of it, to your right, are going to be greater as well, so we can disregard those. Now we go to the center element again. Is 5 our key? Yeah, it is. We found our integer that we're looking for. Return the index value, which is going to be 3.
Wow, it seems like binary search is very similar to quicksort in that divide and conquer mentality.
It absolutely is,
Oh,
and it's a very efficient algorithm to find what you're looking for.
Well, I think we both learned a lot today, and I hope you've
Think
learned
so.
some stuff too.
Thank you.
All right.